Hello, my name is Robert Busby. I'm going to give a presentation on the Alaska Transportable Array and some of the technical advances that we've learned in executing the project. Hopefully these will be some advantage to other network operators. I also want to acknowledge my co-authors, Casey Adderhold, project associate, Ryan Bierma, Jeremy Miner, and Molly Stats. I want to give you an overview of my presentation. We'll introduce the deployment of the transportable array and its successful installation and operation, and then give you some update on our activities upcoming for this summer, including the removal of about 80 stations. And a third section will highlight some of the technical advances that we've learned in the transportable array. These are primarily selected for their applicability to other networks, and maybe some people can find some use in their own networks. These include ancillary sensors such as meteorological instruments and some data handling related to that. Also the data communications and some tips regarding IT security. And then a device we found very useful, sort of out of band, but state of health monitoring beacon to report on, others might find useful. I'm not going to talk much about the power system, which was a complicated system we established, but it's limited in its applicability to the extreme conditions experienced in Alaska, where the high logistics costs warrant the expense of such a power system. The transportable array in Alaska is a large geographic deployment of a large number of seismic stations. There's about 280 sites with 85-kilometer spacing. Each site has a broadband seismometer, infrasound sensors, pressure sensors, meteorological sensors, and soil temperature profilers. It has real-time communications and was fully deployed in the period between 2015 and 2017, has been operating since. This is a picture of one of the stations in Alaska to give you some idea of the remote conditions. You can see in the foreground a seismometer which is buried in a 3-meter steel-cased post hole that's drilled into the ground. In the middle ground is a fiberglass enclosure which houses the equipment, and on the top of the enclosure is antennas which broadcast the data, as well as a meteorological sensor. In the background is a helicopter used for access. This slide shows the number of stations which will be left after the TA completes the project. Many of the stations have been adopted and converted for long-term use by the University of Alaska, supported by both USGS and the NSF AON program, as well as the Alaska Volcano Observatory, and Canadian stations is supported by the Canadian Hazard Information Service and Geological Survey of Canada. Altogether, about 116 stations have been left. We also upgraded about 30 stations that were existing prior to that to the new sensors and post holes. This summer, we plan to complete our activity with the transportable array. We will remove about 80 stations, disconnecting the telemetry on May 1st and removing the stations by the 1st of August. We'll continue some data curation activities, data collected locally through the end of September, and update that data on the IRIS DMC archive. During the summer, we'll have to practice some techniques which we've developed in the past summer, as well as throughout the year, in consultation with several other operators in Alaska for COVID-19 mitigation. The main mitigation was to simply wait until vaccines were available, and therefore we would not be carrying the virus into these remote villages with limited medical facilities. So we were allowed an extension to defer our removal activities until this summer 2021. We've developed a limited contact strategy where the field team is isolated into a bubble. We limit any engagement with the village personnel. We don't stay in the villages. We utilize field camps and primitive camping. We don't take any commercial flights prior to deployment and use quarantine periods as needed. We also try to do as much advanced logistics, minimizing interaction with villages for supplies and cargo. So we think this will go a long way to keep everyone safe this summer. I'll start the technical highlights by introducing you to some equipment in the station. Again, on the left is a picture of the enclosure that we use. It's quite durable. It can be buried in snow and recover. On the right is shown antennas, including the meteorological sensor, and in the bottom is the power system. So the meteorological sensor that we used in Alaska is the Vaisala WXD 520, and then later upgraded to a 536. We had up to 150 of these sensors, which came from a diverse set of sources, some from NSF, some from the NOAA Weather Service, as well as NASA and the Yukon government. Sensor is a multi-sensing device. It senses temperature, pressure, wind speed, wind direction, humidity, and transmits this data in a serial mode at 1 sample per second as a sort of sentence of data values. It's not individual channels. And we incorporate this within our own station hardware into the data records that you see on the archive. So who uses this data? One of the primary users is the Alaska Fire and Fuels Interagency Department, which coordinates several federal agencies in Alaska, the National Park Service, BLM, and Forest Service on hazards related to wildfire. And these meteorological sensors are used to forecast the ground conditions to anticipate what the hazard is in the fire season. So it's good uptake of the data that we recorded for a different purpose. And I want to talk a little bit about the key factors in that data integration and uptake within the seismological community. Any of these ancillary sensors and their channels, it's important to have a common time label that is the same time clock that is used by the seismic data, so that you can compare correlations between the data. And then another key advantage is using the same data format, in this case mini-seed, so that users can switch between different phenomena using the same programs and data handling techniques. For other users outside the seismological community, interdisciplinary users, this data was filtered and then downsampled to a much lower sample rate of 1 sample every 5 minutes. And then it was reformed into a data format that's used by NOAA in their MADIS data assimilation software pack, so that it could be automatically read by several users, including this Fire and Fuels agency. So it's important that the data is able to be recognized for what it is and able to be digested by these other users. So you have to make some effort to convert this data into a usable form. I want to talk a little bit about the data communications that we used. In our case, the remote stations, there were not a lot of existing data services available. We utilized primarily the Inmarsat BGAN service at 60% of the stations. About 20% of the stations there was cellular service available through Verizon, AT&T, various other companies operating in Alaska and Yukon. About 15% of the stations utilize a private radio network. Some research facilities had internet that could host the station, and about 10% of the station uses the commercial VSAT service. providing internet access directly to a satellite, usually C-band in geosynchronous orbit. So a key communication consideration in these data links, of course, is the IT security. And we want to just emphasize that many of these remote station communication devices have firmware that has repeatedly been found to contain security holes, undisclosed user accounts, backdoors. And if this device is reachable over the internet, it will be compromised through these security holes. So you cannot guarantee that the configuration of the device will provide security because someone can change the configuration. We utilized VPN tunnels from our network center to a vendor network center, those being Verizon or AT&T or even Inmarsat. And this allowed for secure connection between our network center and the device communication center, such that we could avoid any connection to the public internet. It also provided, as a side benefit, somewhat simpler configuration of the remote device. However, this can make transferring a station or the modem to another operator more complex, requiring configuration changes to occur in a defined sequence so that you don't lose communication with the device and require site. Finally, I want to mention a device that we use for data communication of state of health. So this is a device by a company in Canada, Zeos, and they make a modem called XI202. The key thing about this device is very low power and has worldwide access to communication via short messages on the Iridium satellite system. The company has built up a communication interface to Q330 data loggers, Nanometrics data loggers, and some additional interfaces to Vicella MET sensors or Jenison charge controllers. And this allows the modem to interrogate the station hardware and compact this information into some short blips that go out on the Iridium satellite system, and so results in a very compact telemetry. There are about 4 messages per day, cost only $16 to $20 per month, and these messages can contain information on the mass position or clock quality, battery voltage. Station information is very useful, and it allows even two-way communication, such that you can switch on some devices at the station or even issue a centering command. This is all independent of the primary communication system and allows you to check whether in fact it's the station that's down or maybe just the data communication that's down. The Iridium messages are delivered to the vendor, and they provide this service that then distributes the messages to other applications, including email or a local instance of the application running on your network computers can write a database of information. We use this database to populate web status pages. So it's a very helpful technology and could be useful in other networks. I'd like to take this opportunity to thank the Transportable Array team. They've been a great group of people to work with. We'll be wrapping up our activities at the end of this field season and continuing into the fall, but be finished by November or December of 2021. I thank them all for their efforts. For more information, here's links to the website and email addresses of the principals. Thanks very much.